Have you ever poured what looked like a perfectly mixed concrete slab, only to watch a layer of muddy water mysteriously rise and pool at the surface? That phenomenon is called bleeding. A little bit is a natural part of the settling process, but too much? That's a ticking time bomb for structural disaster, surface scaling, and catastrophic failure. Today, we are diving deep into the science of concrete integrity. Welcome back to the Certified MTP channel, your ultimate resource for material testing equipment, standards, and industry best practices. I'm your host, and in today's comprehensive guide, we are looking at how we guarantee the integrity of concrete. We're going to cover everything from the fresh, plastic state of cement paste all the way to long-term, hardened stability. When we talk about concrete integrity, we are really talking about predictability. Engineers and contractors need to know that the mix design they specify is going to behave exactly as intended, both on the day it is poured and 50 years down the line. To achieve that level of predictability, we rely on rigorous, standardized laboratory testing. Let's start with the immediate concern on any job site: bleeding. Bleeding is a form of segregation. When concrete is placed, the heavier solid particles, the cement, the sand, the coarse aggregates, naturally want to settle due to gravity. As these heavy materials sink, they displace the lighter mixing water, forcing it to rise to the surface. Now, why is this a problem? If the bleeding rate is too fast, or the total bleeding capacity is too high, that rising water gets trapped under large aggregate particles or reinforcing steel bars. This creates microscopic voids and water pockets. Once the concrete cures, those pockets become permanent weak spots. It destroys the bond between the concrete and the rebar, and it significantly lowers the compressive strength of the structure. Furthermore, excessive surface water leads to a weak, dusty top layer known as latence, which is a nightmare if you plan on applying floor coatings or trying to achieve a durable wear surface. So, how do we measure and prevent this? This brings us to our first essential piece of testing equipment: the cement bleeding apparatus. This highly specialized, precision-engineered tool is designed specifically to determine the rate and capacity of bleeding in cement pastes and mortars, adhering strictly to industry standards. Understanding the exact usage of the cement bleeding apparatus is critical for quality control. Here is how it works in a practical laboratory setting. First, the technician prepares a standardized batch of cement paste or mortar. This mixture is carefully poured into the cylindrical test vessel of the apparatus. We then consolidate the mix, usually through a standardized tamping process, to ensure there are no entrapped air bubbles that could skew the results. Once the sample is prepped, the clock starts. The magic of this apparatus lies in its ability to let us precisely measure the volume of bleed water over specific intervals of time. Typically, a technician will draw off the accumulated water from the surface using a pipette every 10 minutes for the first 40 minutes, and then every 30 minutes thereafter, until the bleeding absolutely ceases. By recording the volume of water extracted at these precise intervals, we can plot a bleeding curve. The cement bleeding apparatus allows us to calculate two vital metrics. First, the bleeding rate, which tells us how aggressively the water is rising. Second, the total bleeding capacity, which tells us the absolute maximum amount of water the mix will expel. If these numbers exceed the specified limits, the mix designer knows immediately that they need to adjust the formulation, perhaps by altering the aggregate gradation, lowering the water-to-cement ratio, or introducing chemical admixtures like air entraining agents or supplementary cementitious materials. The cement bleeding apparatus isn't just a measuring tool. It is a diagnostic instrument that saves millions of dollars in potential structural repairs. Enter our second critical product, the cement autoclave, high pressure. This is one of the most robust and impressive pieces of equipment you will find in a materials testing laboratory. Its primary usage is to conduct accelerated soundness tests on cement by subjecting cured specimens to extreme environments. A high-pressure cement autoclave is essentially an industrial-grade, highly controlled pressure cooker. By utilizing saturated steam at incredibly high pressures and temperatures, it forces the rapid hydration of any uncombined magnesia or free lime present in the cement sample. Under normal atmospheric conditions, this hydration process could take years. Inside the high-pressure autoclave, we can simulate years of environmental exposure in just a single afternoon. Because we are dealing with high-pressure steam, safety and absolute precision are non-negotiable. These units are built with thick, insulated steel chambers, rupture discs, safety pop-off valves, and precise microprocessor controls to ensure the temperature and pressure ramp up at the exact rate required by international testing standards. If a cement sample can survive the brutal environment of the high-pressure autoclave without significant expansion or cracking, engineers can sleep soundly, knowing it will remain dimensionally stable in the real world. Now, you can't just throw a block of cement into any pressurized box and call it a day. In the world of construction materials, standardization is everything. That is why laboratories rely specifically on the ASTM-C151 cement autoclave. When a product is designated as an ASTM-C151 cement autoclave, it means it is engineered to meet the exact, stringent specifications of the American Society for Testing and Materials Standard, C151. This test method dictates the entire life cycle of the soundness test. The usage of an ASTM-C151 compliant autoclave guarantees that your heating and cooling curves are perfectly accurate. The standard requires the autoclave to reach a pressure of 295 pounds per square inch, or about 2 megapascals, in exactly 45 to 75 minutes. Once that massive pressure is reached, the ASTM-C151 autoclave must maintain it flawlessly for exactly 3 hours. After the 3-hour hold, the heating element shuts off, and the autoclave must be able to cool down so that the pressure drops back to less than 10 pounds per square inch within an hour and a half. This strict thermal and pressure cycle ensures that test results are uniform and reproducible, whether you are testing cement in New York, London, or Tokyo. Using an ASTM-C151 certified machine removes the variables, ensuring the cement passes the ultimate test of integrity. But how do we actually put the cement inside this high-pressure beast? You can't just lay the samples on the floor of the chamber. If you do, they'll sit in cooling water, they won't heat evenly, and your test results will be completely invalid. That's why the final piece of our testing puzzle is the cement autoclave test bar holder. The cement autoclave test bar holder is an unsung hero of the testing process. Its primary usage is to safely and securely hold the molded cement prisms, usually up to 8 bars at a time, in a vertical orientation inside the autoclave chamber. This specific vertical positioning is crucial. It ensures that the saturated high-pressure steam circulates freely and evenly around all 4 sides of every single test specimen. Furthermore, these test bar holders are manufactured from specialized high-grade materials that will not corrode, warp, or react chemically when exposed to 295 pounds per square inch of boiling steam. If the holder were to warp, it could bend the cement prisms, giving you a false positive for expansion. By using a certified cement autoclave test bar holder, you ensure your specimens remain perfectly suspended, yielding data you can trust with absolute certainty. Building infrastructure that lasts centuries requires a two-pronged approach. First, we use the cement bleeding apparatus to master the wet plastic phase, ensuring perfect placement, superior rebar bonding, and flawless surface finishes. Then we look to the future. We utilize the high-pressure ASTM-C151 cement autoclave and the precise test bar holders to simulate decades of chemical reactions in a single day, guaranteeing the hardened concrete will never expand and destroy itself from the inside. These aren't just testing machines. They are the guardians of concrete integrity. They give architects the freedom to design, contractors the confidence to build, and the public the safety they deserve. If you are running a material testing laboratory, managing a cement plant, or overseeing large-scale civil engineering projects, you cannot afford to compromise on your testing equipment. You need precision, durability, and strict standard compliance. For the highest quality cement bleeding apparatuses, high-pressure ASTM-C151, cement autoclaves, autoclave test bar holders, and thousands of other premium material testing products, you need to visit CertifiedMTP.com. We supply the industry's best tools so you can achieve the industry's best results. If you found this deep dive into concrete integrity helpful, please hit that like button, subscribe to the Certified MTP channel, and ring the bell so you never miss an update on the tools that build our world. Have a question about ASTM-C151 or bleeding rates? Drop a comment below and our experts will help you out. Thanks for watching, and we'll see you in the next test.